Today's lesson is going to be about finding limits algebraically. So let's start with this true or false question. In order for the limit as x approaches c of f of x to exist, f of c must exist. Well, let's consider the picture here. So if I draw a curve or a line, doesn't matter, f of x, and that has a hole. In this graph, f of c would not exist. It would be undefined. But however, the limit as x approaches c of f of x would exist. So in a situation like this where we have a hole in the graph, it is true that our limit as x approaches c of f of x would exist while f of c does not exist. So this statement is false. We do not have to have an output of the function in order for the limit to exist. So as we talk about finding limits algebraically, what you first want to do is just plug in and see if we can find a limit that way. So if I plug in this pi here, I'm going to have sine of 3 pi over 2 all over pi squared. So I can evaluate sine of 3 pi over 2 as -1 and -1 over pi squared. That's a real number. So this limit does exist, and I could find that limit simply by plugging into the function. Let's take a look at the next one. So something different is going to happen here. So I'm not going to write next to the limit. I'm going to write beneath, and I'm going to plug in that -2. So plugging -2 into the numerator, I'm going to get 0. Plugging -2 into the denominator, I end up with a 4 plus 4 minus 8. So plugging in -2 to the numerator and denominator, I end up with 0 over 0. So what this is called an indeterminate form. So our limit might exist, but the form that we currently have, 0 over 0, can't tell us what the limit is. So what we never want to do is we never want to say that the limit is equal to 0 over 0. Because in a minute you're going to find out this limit does indeed equal something, and it is not equal to whatever this 0 over 0 expression is. So I'm going to get rid of that. Don't ever equate your limit to 0 over 0. So I just did some work off to the side here, and I ended up with this indeterminate form, but that is not my answer. So let's read what it tells us on the page here. When you are unable to find a limit by plugging in, try to simplify the rational expression algebraically. So you'll see that we have the same problem that we just talked about. And what we can do is we can rewrite the limit notation here and do some factoring. So I'm going to factor a negative out of the numerator. So factoring a negative out of the numerator leaves me with a negative and then an x plus 2. Let's factor the denominator by using the product sum method. So here's my expression after I'm done factoring. Now if you notice, we can cancel this out. And so I'm left with the limit as x approaches -2 of -1 over x minus 4. As you work, be sure to write the limit notation in front of each step. So if you recall from previous courses, when we have a factor that cancels out of the numerator and denominator, that means that there's a hole in the graph. And similar to this situation we looked at up here, our limit can exist even if there's a hole in the graph. So by canceling out, we're getting rid of that hole so we can plug in and find the limit. So now that that hole has been canceled out, I can plug in a -2 in place of x, and I'm left with positive 1/6. So my limit does indeed exist, and it equals 1/6. Okay, the next one over here, let's go ahead and see if we get an indeterminate form when we plug in. So plugging 5 into the numerator, I have 5 minus 5, which is 0. Plugging 5 into the denominator, 25. 12 times 5 is 60. So 25 minus 60 is negative 35, plus 35 is 0. So I do have an indeterminate form, but I try to make sure I do that work off to the side and not setting the work equal to the limit. So you would not want to do an equal sign here and equate that limit to 0 over 0. But what we can do is we can say that this limit is equal to the limit as x approaches 5. And now I'm going to factor the numerator and denominator. Okay, in the numerator, let's factor out a negative again. That allows us to just flip the order of those terms. In the denominator, let's factor using product sum method. So factoring, we are going to get x minus 7, x minus 5. So these terms here are going to cancel, and then we can plug in. So in the numerator, I have a negative 1, and then in the denominator, the 5 minus 7, that simplifies to 1/2. Let's look at a couple different ways to simplify these expressions algebraically. So what we have next is called a complex fraction. As you can see, we have a smaller fraction inside of the big fraction. So let's go ahead and plug in and see if we get an indeterminate form. So in this problem, we're plugging pi in place of x. So in the numerator, we have pi minus pi, which equals 0. In the denominator, we have 1 minus pi over pi. So that's basically the same as 1 minus 1, which is also 0. So on this example, instead of factoring the numerator and denominator, to simplify the complex fraction, we're going to multiply by the baby denominator. I call this a baby denominator. So that's the small denominator in our complex fraction. So we're going to multiply by that baby denominator of x in the numerator and in the denominator. So I'm going to rewrite the limit notation. I'm not going to distribute through in the numerator. You'll see, because we'll get something that cancels in a second. So instead, I'm going to leave that as a product. In the denominator, let's go ahead and distribute the x through. So multiplying the x through, we're left with x minus. And now when I multiply that x times that pi over x, those x's cancel. So in the denominator, I'm left with x minus pi. I'm going to make this a little bit skinnier. Let's see if, oh yeah, I'll be able to write a little bit better now. So now, taking a look at our expression, we're able to cancel these out, and all we have left is the limit as x approaches pi of x. And we can plug in the pi now, and we have no funny business like 0 over 0 or even a 0 in the denominator. So when we have a complex fraction, we're going to multiply by the baby denominator. Okay, the next example, we don't necessarily get the indeterminate form 0 over 0 when we plug in, but if I were to plug a 0 in here, I would just have 1 over 0. That's undefined. That makes it difficult for me to work with and find my limit. So I'm going to go ahead and employ that same method as previously. Since we have a fraction in a fraction, we have a complex fraction. So identifying your baby denominator, we're going to multiply by that baby denominator on top and bottom. Let's rewrite our limit notation. And let's multiply on top. Well, x times 1 over x is just 1. Let's distribute through on the bottom. So distributing that x through, we're going to end up with 3 minus 5x. So we don't have anything that cancels right now, but we're able to just plug in the 0 for x and get an expression that simplifies quite nicely. So we get 1/3. So important when you're doing these algebraic limits that you carry the limit notation through each step. So as long as you still have x's left in the problem, you need the limit notation. You can lose that notation when you get down to the step where you're plugging in. Okay, these last three are just a little bit different methods of factoring that we're going to use to evaluate our limits. So on the first one, you should always check and see if you get an indeterminate form, because sometimes it's not an indeterminate form. You can just plug in and get your limit. But plugging in the numerator, you can see we get 0. Plugging a 2 in the denominator, we have 16 minus 6 minus 10. So that does give us an indeterminate form. So let's go ahead and proceed with our factoring. So in the numerator, I'm factoring out the negative, so I can flip the order of those terms again. And now I'm going to do some guessing and checking in order to factor this. So since 4x squared is not prime, I'm going to try 2x and 2x, and then just try some factors here and see if anything works. So I'm looking for pairs of numbers that multiply to 10. And when I multiply them together, I need to get this expression 4x squared minus 3x minus 10. And if I try a few things here, well, here if I look, my outer product is going to be 10, and the inner product is 4. There's no way to add or subtract 10 and 4 and get 3, or negative 3. So that's not correct. In fact, no matter which of these options we try, it's not going to work. So what I'm going to do is I'm going to go back here where I had the x, or the 2x and the 2x, and I'm going to try 4x and x. So let's see if we can place any factors at the back of those binomials in order to get this to work. Well, it's going to work if we put a 2 here and a 5 here. So if I make this 4x plus 5 and x minus 2, what you'll notice is our outer product is negative 8x, and our inner product is positive 5x. When you combine those, you get the 3x here that you want. So we just had to do some guessing and checking until we get the factoring to work out. And now we can go ahead and cancel out the factor of x minus 2. So that leaves us with the limit as x approaches 2, negative 1 over 4x plus 5. To evaluate, we merely plug in the 2 for x. And our limit equals negative 1 over 13. Okay, on the next one, if we plug in a negative 3 in the numerator, we get 0. Plugging in negative 3 in the denominator, we also get 0. So we need to do some factoring. So what we're going to do is we're going to factor that denominator because it's a sum of cubes. So factoring a sum of cubes, I'm going to first take the cube root of the x cubed plus 27. And then I'm going to have x squared minus 3x plus 9. I'll post another video for factoring a sum or difference of cubes if you want to watch it. So these cancel out, and then in the numerator, we're left with a 1. And then we can go ahead and plug in. Negative 3 squared is 9. We have another plus 9 equals 1 over 27. Okay, and lastly here, we're going to find our limit as x approaches negative 5. We should try to plug in and see if we get an indeterminate form. So plugging in, we get 25 plus 15 minus 40. In the denominator, we have a negative 125. 5 times 20 is 100, so 5 times 19 is going to be 95. So plugging in negative 5, we get 95 plus 30. So plugging into the numerator and the denominator, we do get an indeterminate form. So what I'm going to do to factor this denominator is use a little synthetic division. And let me go ahead and factor the numerator, and then we'll talk about that synthetic division. So I'm going to factor the numerator as x minus 8, x plus 5. So I want to not have an indeterminate form. So I'm really hoping that I can factor out an x plus 5 on the bottom so I can cancel that x plus 5 in the numerator. So I'm going to do synthetic division and put a negative 5 here. I'm going to take this guy's coefficients and write them across here. The 0 comes from the coefficient of the x squared. There's no x squared in that term, so I'm going to put a 0 there. So here's how we do our synthetic division. Bring the 1 down, multiply to the negative 5. We go down and we add. I multiply the negative 5 and negative 5, gives 25. We go down and we add. I multiply the 6 and the negative 5. And we go down and we add, and those cancel, leaving us with a remainder of 0. So we did find the right thing to divide by, and we're left with an x squared minus 5x plus 6. The x plus 5's cancel. And then I can plug in that negative 5 into what remains. Let me just zoom in here a little bit and kind of box in this problem. So this leads to negative 5 minus 8 in the numerator, 25 plus 5, 25 plus 6 in the denominator. So I'm plugging in a negative 5. So it leaves me with negative 13 over 56. So that's how we can use synthetic division to factor that denominator and simplify our expression.